All right, so today is our summary of curve sketching. And what that means is we're going to take everything we've done for the past 2 weeks and combine it all together. Now, the good news is you don't have to learn anything new today. The bad news is it's going to be a long problem because we're going to take everything we've done over the past 2 weeks and do it all in the same problem. So the notes part today is very short. I just want to kind of review the things we've done and talk about the order you do them. So basically, if you want to sketch a graph, the first thing you do is what we just did in part 1 of the notes from this section from 5.6, and that's find the asymptotes. Figure out any vertical, any horizontal. You can do end behavior while you're doing the horizontal. All of that is in your notes already, so if you need to review that, go back and look at 5.6 part 1. Once you have that, you're going to do the first derivative test. You're going to find out where this function is increasing and decreasing, where it has local minimums and local maximums. And again, you already have a video on that. If you want to review that, go ahead and watch it. Then we do concavity, which is the same as the first derivative test, but using the second derivative. And that'll give you concavity and inflection points. And by then, you actually have more than enough. I mean, honestly, you could probably sketch the graph after step 2. The concavity is kind of extra, but since we're learning it, I'm going to ask you to do everything in every problem. So the goal isn't just to sketch the graph. The goal is to sketch the graph and tell as much information about it as you can, which will be asymptotes, end behavior, increasing, decreasing, minimums, maximums, concavity, and inflection points. And by the time you've done all that work, remember, these are going to be very long problems. By the time you've done all that work, it'll be very simple to sketch the curve. And then just as a reminder also, step 1 is already done for you guys, because the way I set up the homework this time, in part 1, I gave you a set of problems and I had you just find the asymptotes, because that was new for part 1. Now for part 2, you're doing the same questions and you're finishing them. So don't redo the asymptote work. That's done. Just take your homework from part 1 and continue the problem from there. So I'll start our example today on step 1 to show you the whole problem all the way through, but really you're starting on step 2 today. So here's our example. There's only one of them today because these are very long, you'll see. And it just says to sketch the graph. Now we are sketching completely by hand, no Desmos, no graphing calculator, anything like that. We should be able to do this entire thing with just a piece of paper and a pencil. So keeping that in mind, let's walk through our steps. And step 1 is the asymptotes. So you can do them in either order. I'll go ahead and do horizontal first. And for the horizontal asymptotes, you're going to do the limit as x approaches both positive and negative infinity. This is horizontal, it's also end behavior. So let's start with the limit as x approaches positive infinity of f of x. Now, we have this kind of concept of plugging in a really big number. And when you look at this, yes, it does go to infinity on top and bottom. So I would probably do L'Hopital's rule here. I'd say I'm getting infinity over infinity if I'm plugging in infinity. So I'm going to take the derivative of both sides and try the limit again. Not both sides, sorry, top and bottom. The derivative of x minus 1 is 1. The derivative of the derivative of x squared is 2x. And this time, if I plug in that really big number in the bottom, I get 1 over infinity, which remember equals 0. So that's my first answer here. This has a horizontal asymptote at x equals 0. Now, remember what I talked to you guys about in part 1. There's really a second part to this question where you do the limit as x approaches negative infinity. And then what I would have if I did that is I would get negative infinity on top, positive infinity on the bottom. It doesn't matter, it's still L'Hopital's rule. So I take the derivative and then I get 1 over negative infinity, which also equals 0. So remember what I told you in part 1. For now, if you get a horizontal asymptote, it's going to be the same on both sides. I'll let you know when we start seeing functions where you could have different ones on each side. So I definitely have a horizontal asymptote at x equals 0. Now let's try vertical. Now, vertical asymptotes have to do with domain. So the first thing I do is I check where this thing is undefined, and it's undefined at x equals 0. That's the only place it's undefined, because the denominator is x squared. If I plug in 0, I get a 0 in the denominator. So what I want to do now is do the limit as x approaches 0. And remember, if you want to review any of this, I'm going quickly because this is our review. If you want a better view of this, go back and watch the part 1 video again. I talk more in depth about this. But if I plug in 0 for x, if I do direct substitution, I get negative 1 over 0. Any constant over 0 means yes, that number does represent a vertical asymptote. So we actually have for this one, that would be y equals 0. We actually have for this one a horizontal asymptote at x equals 0 and a vertical asymptote at y equals 0. 0 and 0 for both of them. All right, that's step 1. We have our asymptotes. And remember, for homework, you've already done this part. So you're ready to, you're going to start homework from here. All right. So this is what we have so far. Here's our function. I copied the function in the top corner so we could use it. And I'm just kind of keeping track of our answers so far because I need blank screens. It takes a lot of space to do this. So the next step is to do the first derivative test, which means I need to find the first derivative. So let's do that next. Let's find f prime of x here. And that's going to be quotient rule. So let me start off by squaring the bottom, which would be x to the 4th. And then I have the derivative of the top, which would just be 1, times the bottom, x squared, minus the derivative of the bottom would be 2x, times the top, which is x minus 1. So if we clean this up a little bit, we have x squared minus 2x and plus 2. And it's all over x to the 4th plus 2x. That's 2x squared, actually. Okay, that's better. So what we end up with is we have negative x squared plus 2x over x to the 4th. Now what I'm going to do, I'm going to go one step further here. I see x's everywhere. So let's actually factor an x out on top, which would give me negative x plus 2. And then we can cancel it with one of them from the bottom. So what I'm going to get for my final f prime of x is negative x plus 2 over x cubed. All right, now from there we are going to find critical values. Critical values happen wherever the top or bottom equals 0. So I'm definitely going to get one critical value at 0. And for this x right here, looks like I'm going to get positive 2. Because if I plug in a positive 2, I would get negative 2 plus 2 is 0. So my critical values, the two things I want to put on a number line are 0 and 2. And we will test intervals in the purple function over there. So let's start with any negative number, like negative 10. So if I put in negative 10 on top, that becomes positive 10 plus 2, which is positive. And on bottom, negative 10 cubed is negative. Positive divided by negative is negative. So it's negative here. All right, for my middle interval, I would probably pick the number 1. It's the only whole number in there. Negative 1 plus 2 is positive. 1 cubed is also positive, so it's positive in the middle. And then we need a big number, a big positive number, anything bigger than 2. So let's say like 10. Negative 10 plus 2 is negative, and positive 10 cubed is positive. Negative divided by positive is negative. So what we have is a function that is decreasing, then increasing, then decreasing. Now, from the work, it looks like we have one minimum and one maximum. But remember, 0 is our vertical asymptote. So 0 cannot be a minimum or a maximum. And if you didn't remember that, it's okay, because on the next step, like when let me do the 2 first. The 2 definitely is a maximum. And to figure out the value that goes with it, I go back to the original function up in the top right corner there, and I plug in 2. That would be 2 minus 1 over 2 squared, 1/4. So 2 comma 1/4. Now, if I had tried to find the other one, like if I said, okay, now there's also a minimum at 0 comma something, then I get 0 minus 1 over 0 squared, and I realize, oh no, wait, that was undefined, so it's not really a minimum. So even if you didn't remember that was an asymptote, the work's going to tell you it is anyways. So basically this one has a maximum at 2 comma 1/4 and nothing else. All right, so here's what we have so far. We have our original function and our derivative. We have a horizontal asymptote, we have a vertical asymptote, and we just figured out we have a local minimum. Let's now do the second derivative and figure out our concavity. So for second derivative, I'm going to find f double prime here. And that's going to be quotient rule again. So if I square the bottom, I get x to the 6th power. And then I do derivative of the top would be -1 times the bottom, x cubed, minus derivative of the bottom by power rule would be 3x squared times the top, which is -x plus 2. Clean it up a little bit and you get -x cubed plus 3x cubed minus 6x squared, and it's still over x to the 6th, or 2x cubed minus 6x squared over x to the 6th. Now I have some x's again. In fact, I could factor out an x squared and cancel those, so let's do that. If I factor out x squared on top, it leaves me with 2x minus 6. And then the x squared cancels with 2 of them on the bottom and would actually leave me with an x to the 4th. So what I'm going to get for my final second derivative here, f double prime, is 2x minus 6 over x to the 4th power. Which means for critical numbers, I'm going to get 0 again, even though we know that's not going to be an inflection point, that's an asymptote. And on top, I would get positive 3. Yeah, 2 times 3 is 6. 6 minus 6 would give me the 0. So those are the numbers I'm going to test this time. I have a 0 and a 3. That creates my intervals. Now, a little bit of a shortcut here. This didn't work last time. On the first derivative test, we had x cubed in the bottom, which could be positive or negative. But see, now I have an x to the 4th, which is always positive, so I can ignore that and basically just test the 2x minus 6. So if I put in a negative number like -10, I would have -20 minus 6, definitely negative there. If I put in, I can choose 1 or 2, let's choose 1 for the middle interval. 2 minus 6 is -4, still negative. And if I put in a big number like anything bigger than 3, like 10, 20 minus 6 is 14, that would be positive. So the only inflection point I have, see, 0 doesn't even look like an inflection point. It didn't change anyways, but it was an asymptote, so we already knew it wasn't. So in this case, it looks like the only inflection point I have happens at 3. And to figure it out, we're going to go way back to the way back to the beginning and plug 3 in. So I would have 3 minus 1 over 3 squared. That would be 2 over 9. And that's the second derivative test and concavity. So basically what we have, we've done a ton of work. We've done more than enough work. Remember, I told you really after the first derivative test, I probably could have drawn this graph. But now we're really, really sure of how we can draw a really accurate graph. So let's do that. So right here, we have all of our answers, our horizontal and vertical asymptote, our local maximum, our inflection point, and a blank graph to draw it on. Let's start putting some of this stuff on the graph. I have a horizontal asymptote on both sides at x equals 0. So basically, draw a dotted line in there. On both the left and the right, this graph is going to flatten out right on the axis. And I have a vertical asymptote also at 0, which is the y-axis. So same concept. I'm going to be approaching that line from both sides. I have a local maximum at 2, 1/4. Now what I might do, I'm gonna keep my x-axis the same. I'm gonna just number 1, 2, 3, etc. But for the y-axis, since I have some really small y values, I think I'm gonna make every 4 squares count as 1. We'll see how that looks. Kind of zoom it in just to be able to see. And the reason I did that, so my first point is 2, 1/4. That would actually be right here, the way I labeled it. 1/4 would be 1 square. Now my inflection point is 3, 2/9. You have to realize that 2/9 is a tiny, tiny, tiny bit smaller than 1/4. Like with a common denominator, it would be 9/36 versus 8/36. So this point is just a tiny, tiny, tiny bit lower than 1/4. Now, 2 is my local maximum, 2, 1/4. That means from that point, it's turning down in both directions. It's turning down to get to this point, and it's turning down towards the asymptote. So I'm going to actually blend into the asymptote here and basically go down towards negative infinity. Now here's what's important about the inflection point. If I did not have an inflection point there, if this thing was concave down forever, it wouldn't have an asymptote, because that would just keep doing like the same thing as the other side. It would just go like this. But that's not what we want. And the inflection point, because it's going to turn and become concave up, is why it twists there and blends into the asymptote. And that's what an inflection point does. It changes from concave down to concave up. It's a twist in the graph. Now, the only other thing we would have to do is figure out what happens on the left-hand side of this graph. And based on the asymptotes, there's kind of only 2 things that can happen here. It's either going to go from one asymptote to the other like this, or one asymptote to the other like this. We just have to kind of figure out if it's on the top or the bottom. And a good way to do that is just pick any number, plug it into the original function, and see if you're getting a positive or a negative. So like, let's say I plugged in x equals -2 to the original function. I would have -2 minus 1 over -2 squared. That would be -3 over +4. It's negative. So it's the bottom one. So we get rid of this top one, and that's our answer there. So really, from the work we had done, I knew exactly what this graph looked like with one question. And the work I did in green was the only question. It's like, is that other piece on the top of the graph or the bottom? And just a quick plug in for x will tell you which one. So basically that's sketching using calculus, using limits and derivatives. It's a summary of everything we've done this chapter, and it's also a perfect study for the test because it's everything we've done this chapter. So make sure you focus on each step along the way. It's not just about graphing, it's also about understanding asymptotes, increasing, decreasing, concavity, every single step along the way.